So I'll start with a brief overview where we are now, just to remind you of the grand scheme. We are studying dynamical systems. To study them, we have to define the state of possible states, called state space. Sometimes in mechanical applications, as you maybe see even today, sometimes you have some angles floating around and we call it the phase space. So that's what can happen. That's state space. And then if you have a law that tells you for any particular state, there is unique future, that's called a dynamical system. And it's a powerful set of ideas. So the course is almost exclusively framed in this language. Today, we will continue thinking about bifurcations. So we are still in this incredibly simple setting. We have only one dimension, one spatial dimension where we can be. And that makes possible outcomes very simple because you either get stuck in a fixed point, an equilibrium, or you march off to infinity. There are only two possible things that can happen when you are living in a one-dimensional world. But this world can be changed by changing external parameters which define your law. And the families of dynamical systems connected just by changing some parameter undergo what's called bifurcations. So this Euler example is you have a beam, cylindrical beam. Suppose you're in one sideways dimension and you keep putting weight on the tip of this thing. It's maybe an aluminum rod. At some point, the weight is too heavy and the thing buckles. And in this particular case, it can buckle to the left or to the right, and it can assume another equilibrium position, which doesn't have a symmetry that you started with, which was symmetry around the vertical axis. And this weight is external parameter, is something that's not affecting the law itself, but it's a parameter of the law, so put that much weight. And this is called bifurcation from Greek. Start with something and get two more outcomes, two branches of outcomes, bifurcations. And the simplest and the most common one is a saddle node or blue sky bifurcation. So it's a very simple dynamical system in which you have velocity that depends in nonlinear way on where you are, in this case, like x squared, first nonlinear you can have. And the parameter is r. And if r is negative, you have a bottom of the well, but basically you have two solutions for any given value of r. One is attractive, one is repelling, until you get to the critical point where bifurcation, two branches happen, where these guys coalesce, and from left it looks attractive, from right it looks repulsive. But that's a very fragile situation, and if you increase your R a little bit, you have no solutions at all. And this is a quite common kind of bifurcation. For example, if you have a washboard and you throw a little ball trying to hit the edge of the washboard, as long as you're hitting it, it bounces in some way. You go epsilon above it, you miss the hoop, and it just goes through totally different motion. This is, an example. So we'll go through a bunch of these examples. They all have names. Don't worry if you forget them. They're every place on Wikipedia or something. Just remember their bifurcations, and then you can look up which bifurcation you have run into. So saddle lock is a very typical one, but sometimes you have constraints. For example, the number of something can be only positive, or only the living can reproduce in population dynamics and biology context. In this case, you have to impose something. For example, here you impose a fixed point. So x equals 0 is always a fixed point. And then you have parameter that tells you where the other fixed point of parabola is. And you go through the same kind of bifurcation as we thought, but while this is happening, one fixed point is always there. You cannot avoid. An interesting thing that we learned there is that sometimes, quite often, something that used to be stable is still a solution, but it's an unstable solution. Whereas something you didn't pay attention to because it was unstable, at critical point gets converted and into stable. And that's why this name, I guess, comes on trans being beyond the critical point. You have stability. People psychologically tend to think that stable is good and chaos is bad. And this is a very limited point of view. If you understand chaos, you can use it for ends, evil or good. That depends on you. But if you understand it, you're much powerful in that. So it's not necessarily bad. But psychology is, always find stable solutions. And now we will go through a few more of these solutions that everybody sooner or later runs into. So the one that's really, really popular, especially at times of upheaval, is pitchfork. In French Revolution, pitchfork was a preferred way for peasants to express their opinions. And in the present context, it's a thing that just we kind of looked at, often is used to describe buckling, for example. And it has several varieties of it. So one is called super critical. And again, if you forget what precisely is super as opposed to subcritical, a few weeks after the course is over, it's okay. That's easy to look up, but the concept is very important. So you have an equation, the law, that says the velocity that you look at has a term proportional to x and the term proportional, there's a parameter r. So we are writing a normal form, the simplest version of this thing, which is cubic. Now, why would you get into cubic when quadratic is just as good? Well, when you're buckling beams, there is no reason to prefer left or right. That's your convention, but the system doesn't care. So whether this thing buckles this way and that way, it'll have the same curvature and same shape and same kind of elasticity up to a reflection symmetry. So if I change x to minus x, this will get it into the other solution. So this is extremely common situation. Happens all the time that you don't care about left or right. There is a more magical version of this in mechanics, which is very surprising. The way lots of mechanical systems are written, you don't care what's future or past. The equation looks the same. And this is a source of profound discomfort to lots of people over centuries, because our experience of time is that it marches forward, it has an arrow. But equations don't very often. So you're only allowed to write equations that have a property: if I change x to minus x, I get the same equation. So if this gets replaced by minus x, I'll just get minus sign here. If this gets replaced by minus x, I'll get minus sign. If this gets replaced by minus x, it's an odd power. So that'll also get a minus sign. So the three terms, both, all terms on left and right, get an overall prefactor of -1, which you can multiply out, and you get back to the same equation. So this equation is invariant under symmetry. And symmetry, in this case, has many names, but it's a reflection symmetry. If you change every place your state x for state minus x, equations don't change. That's why it's cube. If I had a square here, this term would not change sign, and I would be not in good shape. So pitchfork bifurcation, the kind of thing you always expect. And this is a general principle. When you write these normal forms, and it goes much beyond this course, it goes to very foundations of how physics works and how the laws of nature are written. The way the laws of nature are written is that you make a list of things that don't matter. They're called symmetries. They're sacred. For example, the law of nature should be same in Atlanta and New York and Dallas or San Jan. So under translation in three-dimensional space, it's the same rule that works. So you're only allowed to write laws in which you don't have explicit dependence on position, only on differences of positions, because those don't change under translation. And one difference of position is what you do when you compute the derivative of a function, because you compute a function close to itself and take a limit. So also derivatives have to obey this. Then you say, well, it doesn't matter what's up or down, left and right, which way I'm facing, which way is planet Earth facing a given instant. So you have to impose rotational symmetry, and you end up with a group which is called Euclidean group of symmetry if you're Newton, or Poincaré group of symmetry if you're Einstein. And that's how you write laws. You just say, I have changes, these little derivatives here right now in time, but there could also be comparison with my neighbors in space. And I now, on the right-hand side, I write everything that satisfies desired invariances. Here is a very simple one. The translation has obviously been broken because I have origin, so it's a special thing. But if this was something about evolution of time, I would not be allowed to have explicit breaking of that symmetry. So it's very deep, and very many physicists in theoretical physics believe that their job is simply to write all this term and rescale, minimize number of parameters, and write supersymmetric D-membrane string theory, something, something, something. And then you go home because you have written the law. Now, in this course, you learn that writing the law is step one. And then there are many other steps because you have to figure out what the law does. My colleague often don't have time for to waste on consequences of that. So they write just another symmetric law. So, I'm not a fan of that particular school. So the other thing that symmetry does is that if you integrate this equation and you get x as a function of time, then it turns out you immediately have two solutions. If you write minus x as a function of time, so instead of going right, you go left. That's what minus means. That's also a solution. So symmetry is a great deal because you got two solutions for price of one. Now, if the symmetry was continuous, like in a hoop example we might do today, you get actually infinitely many solutions if you solve one of them. So symmetries do many good things, but basically they, clear up your thinking and simplify. They eliminate inadmissible wrong formulations of possible laws of nature if they violate the symmetries which must be obeyed, number one. Number two, it's enough to produce one solution in a set of solutions related to symmetries. That can be a great saving. And number three, and we do this without realizing very often, symmetries enable you to make your problem lower dimensional. You can remove dimensions of your problem, like moving around the axis of something, and concentrate only on important things, which is what happens in radial direction. And if you have taken quantum mechanics course, this is basically all you do in kind of soluble problems like hydrogen atom and others. You impose more and more symmetries, and eventually the problem is kind of one-dimensional, zero-dimensional. You solve it, even though you start in many dimensions. So in this very humble example, what do? We know how to do this kind of things. We write one-dimensional problem, x-axis. We plot the velocity for every x. And if r, this guy, is smaller than 0, then what happens is this is negative, this is negative. So when you plot the function, it just looks like that. You start going down, and you keep going down. There is obvious fixed point where x equals 0. There is a fixed point. This fixed point has to be stable because from the left you flow into it. And from the right you have negative velocity, so you flow into it. So for r equals 0, there is very simple dynamics. Everybody dies, goes to the origin. Now you look at the other critical thing. that looks almost the same. Clearly the critical thing will happen for r equals 0 because that changes the stability of the origin, right? So now what happens for r equals 0? You go down, but now you enter with 0 slope, not final slope. Because the r equals 0, this is x cubed, that's very flat. And it looks like the previous case. You either creep from this side or this side. The only difference is that when you come close to 0, if you do this on computer, you'll discover it starts moving very, very slowly. That's called a critical slowdown, and something you have to be aware, because it's numerically a big nuisance, and it's also an important thing physically. Now, if r is positive, parameter, then for very small x, this doesn't matter. I'm moving linearly with r, but it's positive, so I'm increasing. So if I look at what this thing looks like, velocity x again. Here I start out with slope, which is r, with a positive slope. But then this always wins for sufficient large r. So this thing has to bend over and come down. And this, remember, is a symmetric function, x minus 1. So this thing will be flipped this way, and velocity is also flipped. So what used to be going down, it goes up. This is just the, you can turn it by 180 degrees. This is just the same thing flipped around. And now when I look at the flow, I approach this. Here I'm negative, so I go this way. So this is a stable point. Now here, same story. I approach this from this side, I approach it. So why is this a pitchfork? We can draw the function in the way that we'll learn how to do it in the last lecture, which is we can take for the horizontal axis the parameter, because that's kind of important, psychologically important thing for us. And on a vertical line, we can plot position of fixed points. Fixed point or fixed points. And what do we know? We know that when r is negative, we always have one negative fixed point at origin. So we always have attractive fixed point here. When I come through that, this is kind of turned sideways, if you wish, so I have an infinite slope. And beyond that, I have two attractive fixed points. And what used to be stable is now unstable. Origin is always a fixed point. And, you put little spokes here, you have a pitchfork. So unlike saddle node, this actually makes sense. and it's very, very common. It's an important bifurcation. It happens whenever there is a symmetry in the system. A statement with some qualifications, but it's almost always like that. Okay, so now I'll work out an example of a pitchfork that is very neuroscience, because all these things are very applicable mathematics, even though it's so simple and low dimensional. Keep showing up in models of numeric, mathematical description of phenomena, either in neuroscience or in population biology and gene transfer and many other things. So here is the biological thing, or neurobiological. There are things called neurons, and what they have is they have, the neuron. They have a thing called Axion. And they send stuff out by little electrical wires that go out of them. And there are, depending on the neighborhood that you want to include, typically of orders of hundreds of thousands of them to 10 to the 13th of them, depending what you want to do. There are many of them. They're cute. They're a little bit slow, largely. And they are very imperfect. But what they have is they have axions which collect information from their neighbors. So it's a directed kind of network of things. And once the neuron gets really excited, it bursts, not physically, but in terms of electric activity, sends pulses which are collected by axions of other neurons. And together they create this amazing thing that we consider a brain. So that, they have this kind of dendritic structure of many branches being connected. So the first attempt to understand, when there are very many of them, is some kind of average description of how they work. And what we know about them is they're little electrochemical devices. So they have membranes. There is inside of a neuron, outside, and there is electric potential across it. So let's say that there is variable X, which is membrane. And, I don't remember the real units, but I vaguely remember millivolts are typical numbers. I might be wrong. So membrane potential is the difference of, charge density inside and outside a chemical kind of charge density. So there's some voltage across the wall. And then this is extremely complicated, but there are very many of them. So you can build models, and they're quite impressively simple and successful, of individual neurons, but as everybody talks to thousands of other neurons, listens to and talks to other ones, we start averaging these bursts. They're called spikes in the lingo because you put an electrode and a spike shows up in a reading. And we start talking about firing rates. Which is the average number of the spikes in which, this guy has gone bananas and sends information outside per unit time and, times a milliseconds. Up to 200 milliseconds, they're amazingly slow considering that people can actually fly fighter jets with these firing rates, but we manage. So now comes observations, and observations say that if I change the potential, how much I've accumulated charge within a neuron, roughly speaking, and plot this rate of firing, what we find out is that there is saturation rate. So there is something that says that if X suddenly is 10 volts and not millivolts, I still cannot fire faster than something. So there is a natural limitation that has to do with, just chemistry of recharging, which limits the firing rate. And on the other end, if there is no potential, nothing is happening. So here we have a saturation. Here we have dormancy. If nothing much is happening, I expect to be down at 0. And then at some voltage, things start happening. Now this is average, or many neurons expect this all to be very smooth and not particularly sharp. So there is firing rate that goes up and reaches saturation. So very simple function. And now it's simply data fitting, if you wish, but as we are solving this first order equations, typical solutions have to do with exponentials. So it's very natural to say that this is a sigmoid. This is a stupid word. It just says it looks like Greek letter sigma to some people. But what it means in practice that you say, well, the first approximation, I can write the firing rate as hyperbolic tangent. Now, hyperbolic tangent sounds fancy, but all it means is it's a ratio of exponential to x minus exponential to minus x. Tangent is sine over cosine, but when argument goes imaginary, it becomes a ratio of exponentials. And divided by the sum of two exponentials. That's just definition. And then there is some kind of parameter here. There's some width. And there is some width here. Now we're kind of chosen units in which the typical width is controlled by e to the minus x, meaning based on natural logarithms, roughly speaking 2. But then you have to know how this goes. So there is a parameter beta. And now you write the simplest possible model. I don't know who wrote it first. You say the change in potential is usually, when you write this phenomenological equation, you have to write all the terms. The first term, the constant you can usually get rid of by centering this thing, so the constant becomes zero. So there is a linear term, and with linear term, you say, well, it's a biological thing, so if I have some charge inside, it's a leaky membrane. So there is a minus sign here, and by itself, the charge will go away. It'll just leak through. So this is leaky capacitor, if you wish. That's the first term you'll have. And then there is a second term, which is beta times V. And V is this function. So what this term says, this is the input. From other neurons. So here you are, a very simple neuroscience model saying the activity, the change of the voltage in a single neuron will depend on physical and chemical properties of a neuron. So the important thing is that there is leakiness minus sign. And we can always rescale things that, we can get rid of the factors. We can use natural units for voltage for a biological system. So this is just kind of convenient normal form. And then there is what I get from other people, other neurons, and it's hyperbolic tangent. And, don't get very impressed by the word hyperbolic tangent, because all it means is the equation has a property that that for very small activity of neighbors, if you live in a dead neighborhood, then basically nothing happens. It's dormant. But if there is a great amount of activity around you, you're mother of many children, at some point you cannot respond to more input and you reach saturation. So that's all this model says. And now your task as a student of nonlinear dynamics is to say, well, what kind of solutions does this equation have? I was playing fast, so maybe try to tell you what I really was doing. So what I really want to write is that the law is 1/2 tangent plus 1. Activity cannot be negative. I cannot be, well, if you're certain kind of inclination, your contribution can be negative. I totally agree. But as far as neurons are concerned, so this has to go from 0 to maximum, to its saturation point. And tangent, of course, has ranges that if you go very far to the right, you can omit these two terms and you go to value 1, right?
Yes.
But if you go very far to the left, you can omit these two terms, and then you have -1 as a value. So you should really add 1 to this and maybe stick 1/2 someplace to get a nice sigmoid that you want, to saturate, to go from 0 to 1 let's say that this is a motivation for this particular equation, even though if I did neuroscience, I would have to screw around a little bit more. But we'll just look at this. I just wanted to tell you where the sigmoid comes from, but it didn't want to go into more detail. So we'll look at this equation. So we are looking at x dot equals minus x plus beta x. And we have again the three cases. Beta smaller than 1. If beta is negative, and then for small x, what happens for small x is that tangent of h, this thing is, for small x, it's number 2, they're roughly 2. Here, the leading term in Taylor series cancels, and this is proportional to x. So close to the origin, the beta x let's call this y and x. This has slope 1. And then we have to balance with minus x. So let's look at what this is. Then at beta equals 1, these guys exactly align. So I'm doing this trick. I'm plotting this as separate functions, and then I care about the difference. So what happens here, it's a criticality, means that the hyperbolic thing exactly aligns. And when beta is larger, not only does it align, but it does things like that. It's steeper, but it has to saturate, come from no place. So it has to have fixed points. And suddenly there are 3 fixed points. Criticality there is 1, below criticality is 1. And I remind you what the pitchfork bifurcation looked like. Similar plots that kind of turn sideways because I have to subtract a linear term. And this has a property of pitchfork bifurcation, meaning when beta is, you're not listening to anybody, you just die, then there is this funny critical regime, which happens for very special value that equals 1. And above, you find yourself in either 2 states. You're kind of bistable. And that's a big deal in neuroscience. We find out that when B is sufficiently positive, we have not 1 but 2 stable solutions. So their firing rates can be either low or high. They're both equally good solutions. And it sort of depends a little bit at what firing rate your system started. So here, below neurons, so small beta, they just fire. But here you have two possible situations. Your membrane potential is either large or small. In this case, if you go for large values, they asymptote. They kind of move around eventually on the straight lines because, sigma it becomes flat at a large value. This is the first kind of thing where you can see that some of the simple tool of nonlinear dynamics might not be only for applied mathematicians, but for people in wet labs and thinking about third millennium kind of problems. So this is pitchfork bifurcation in neuroscience. Now, people who don't care about neuroscience but care about, let's say, quantum mechanics will also run into it, but it'll have a different name. So Strogatz has an example of that kind. 3.4.2, which is the potential. So in condensed matter physics, we tend to play with potentials. Quantum mechanics and such. And if you can write your equation x dot, which has this phenomenological normal form minus x3, if you can write it as a minus a gradient of a function, potential function. In this very simple example, it's obvious what this is. This is polynomial, so if I integrate it, I can write the potential. So I can just write it out. Here is my parameter term, and it gets multiplied by x squared, because when I take a derivative of it, it'll cancel this too, and I'll get that thing there. And to get this term, let's just write 1/4 x to the 4th. Now, writing problems in potential form is very nice, because you can see that the potential, and that's a guiding principle of writing Lagrangians, Hamiltonians, and fancy particle physics equations. You see explicitly that if x goes to minus x, so if I replace x by minus x and substitute it every place, the potential doesn't change. It's an invariant of potential, so it's very obvious. And this is kind of things you'll see always in physics applications. You'll have some one-dimensional problem of on a lattice or something, and graphene, I don't know what. But potential will have to be fourth order unless you stick a magnetic field and change, left and right rotation senses. And now you can do the same thing as you did before, but it's in a way that physicists like to draw it. So they'll look at this potential, V of x, and they'll look at what it looks like for 3 parameter values. So what does it look like for R negative, R critical, or 0 in this case, and R positive? And this is just quadratic and quartic function. So it's clear that when x is large, this thing rules. When x is small, it depends on this parameter, which one is more dominant. Basically, when x is more locally, everything is a parabola. So when r is negative, this is positive, this is positive. So we know what this looks like as a function of x. Just has to grow on both sides. Then we have this critical situation that at this point, the function, even when you take a derivative of it, the derivative is 0. So it's a critical situation. When you plot it, it looks very flat at the bottom. But if this is positive, then in the beginning, I have an inverted parabola. So I start out this way until x gets large enough that these two guys are comparable, that you compute by taking derivative of this and making it 0. So it's flat at the bottom. That's easy to compute. And beyond that, x to the fourth always wins out, no matter what. And you get famous bistability. In potential picture, it means that you get bottom of the well not here. This is now unstable. You get it here. And you find out that there are two possible outcomes to everything you do. And they're stable. So this system is bistable. And now in neuroscience, this is sort of beginning of the main ideas of how do you train, or machine learning, how do you train systems to remember something or identify something. The simple example is bistability, saying you train it to say, I'm either on the left or right in these two values, and they mean something, I either see a cat or don't see a cat, some binary thing. Now comes one of these words again. It's subcritical. And that one is less pitchfork intuitive. Before, we had a minus sign here, and its purpose was to, produce these solutions. But this sign could be positive. So what happens then? Now, R goes through its usual things, but this thing doesn't stabilize like it used to, because before, when X was big enough, this was negative sign, so the velocity would be slowing down. So I was always being pulled back in, not allowed to run away. But now when X gets large, you say, okay, go for it, faster, faster, faster. So now if you do the usual plot that we plotted before, where you put here your parameter, now what happens for positive values? You find there's only one solution that's unstable. When you look at negative values, you find one solution that's stable. And now the pitchfork is going the wrong way. So there are three branches, and for negative R, these branches exist, because if this is negative, you can balance x cubed and this term to get 0. So that's what defines the branches. And they are, you can, they're obvious from this formula. They are at square root of minus r and minus square root of r. And origin is stable, because if r is negative, this is slowing you down, and this is small, insignificant. But when r is positive, nothing is stable. And if you really work very hard, you can find one solution, which is unstable one. So if you do the plots we have done before, let's see, for this value, just then, what does this function look like plotted out? If I plot x dot as a function of x, then this function, it's cubic. For large x, it goes up there, so it has to go someplace this direction. But that means this is an unstable point. That means that in this interval, you're floating this way or that way. And it has to go through 0. It's cubic, so it has to go to large negative values over here. And voila, this is unstable because you go away from it. That's what's happening here. And there is only one stable branch. Now, the real life is not like this. What we know in real life is that eventually common sense will prevail. For example, I will not be able to accelerate and go beyond the speed of light. Something will happen. So you have to model that. And how you model it is you add another terms that you only notice when you're far away from your small neighborhood, which things are looking like a pitchfork. So what everybody does is to say, well, close to my little neighborhood, when r is very small, thing looks like that. There's a competition between x and x cubed. But if I go further out, x grows, a new Bohr block comes in, which says calm down. So there's a minus sign, and it has to be fifth because all of these powers can be odd to satisfy reflection principle. Remember, x to minus x is what defines pitch for bifurcation. So now if you study this system, here is your r, and on a vertical axis, you plot the fixed points. What happens is for the small x and close to origin and negative r, we have that stable fixed point. Remember, we had it here. That one gets converted to unstable fixed point. It's still there always, but it's unstable. Now there are these two unstable branches. But now what happens, I've added another thing to it in such a way that, it prevails, the fifth term prevails on point Russell zone, the cubic term, so there'll be more fixed points. And when you work it out, the way it works out is that actually there is another value of your parameter, which you didn't realize before, but you discovered experimentally. So this literally what happens when we study turbulence. We have some solutions which are very calm, but when we kick them, suddenly it turns out there are solutions very far away, which are blue sky kind of solutions. And what happens with these solutions is that what used to be unstable, when you go far enough, becomes unstable. And what used to be unstable is converted into stable. So you find out that with the fifth term, there are all kinds of new regimes. So there is a regime when you have 3 stable points and 2 unstable points. There's a regime where there's only 1 stable point. No matter what you do, everything dies. But then there is a regime that either you die close to the neighborhood or you run away very far, but then you get stuck into another attractive point. And when this one peters out, you go through an inverse bifurcation. Don't worry, because if you run away from this, you'll get caught either on the upper or lower stable branch. And so I will not have time to do the thing called bead on rotating hoop. I recommend you go through it, especially if you were having trouble with the problem 1, with the pendulum problem. It's a very nice problem to work out, mechanical problem of bistability. So I recommend it, but I won't do it. I just want to remark one more thing right now about this kind of equations. And that's done as exercise 3.5.8. That, every time you add a new term, in principle, there is a new parameter in the problem, because you have to say how strong the new term is. So it's not that you just have R, single parameter, but there could be B times X and C times X to the 5. And then what you can always do to go back to a normal form of something as simple as possible, you can try to rescale everything you can possibly rescale to decrease the number of parameters by noticing that under rescaling, some parameters cancel. So for example, if you take X and replace it by 8 times X in your equation, and if you take your time, this is dt over dx over dt, and you replace it by b. Now here you have to be very careful, because you want to reverse direction of time. So you have to make sure that b is positive. Then what will happen, this equation will get extra stuff in it. A, B. This term gets an A in front of it. So this is R times A. This term will get a cube. This term will get a to the 5 prefactor of x and x cube and x5. And now what you can do is you multiply both sides by this factor. When you do that, you get B here in front of R. Then you get A squared, because you lose one of these guys, times B. X plus x to the 5, and here you get A4 times B. And now you just rename these guys, give them new cute little new names. So you call this combination, you just say, well, that's something I'll call A. Plus, there was a minus sign here, sorry, minus. Call this C times X5. And what's the point of this? It just says that this system in real life, you'll have to measure 3 parameters, phenomenological parameters, to describe it, but no more. Could be 4. So one thing that you always want to do, then you can eliminate one of these guys and you will eventually find out, so do the exercise, we'll find out actually these problems which have so many branches only need 2 parameters.
Time derivative.
Oh, I'm wrong. God, thank you. Of
No
course.
problem.
It's T. Oh, God. You're right. I often intentionally make errors, but I'm really good in making unintentional errors. That's
Okay, thank you, Professor.
Thanks. Everything you said was correct. Everything I wrote was wrong. So you should feel good.